Okay, quantum physics, my realm. I love quantum physics, and this guy apparently does too, Philip Ball. He says quantum mechanics isn't weird, we're just too big. Let's listen to what he has to say.
The stage is yours.
Thank you, Zako. Well, in this talk, what I want to do is to ask the following question. What does quantum mechanics mean? Well, without further ado, let me just skip to my conclusions. Nobody knows. Thanks for...
Now, you go on to Yale University, the professor gets up there, the first thing is he says, we're going to have a great time about quantum mechanics, but I have good news and bad news. The bad news is that quantum mechanics is literally impossible to understand. The good news is that nobody understands it, so it doesn't matter. All you got to do is write what I tell you and you're going to pass. Well, let's look at quantum mechanics, because I can actually see it. Okay, my friends, Roger once again. This is going to be an absolutely fabulous, wonderful, delightful presentation, to me anyway. That is all that exists in the universe. Case closed, we could stop right now, but as I never do stop early. What is that? That's light. That is light. And everything there is made of light. Protons, neutrons, molecules, eyeballs, everything there is, toenails, everything there is made of electrons. And those electrons fit together in the new model called electron flood theory. Bohr is no more. The new electron flood theory, Bohr is boring. Everybody's discounted Bohr now. They know it doesn't work. One gigantic positive core and a bunch of little negatives, they go together. It's been insanity. I've known this for 50 years. I've been fighting against the system, and now I have the proof to show that I'm right. And you guys were all wrong. So there. Now, what is light? I'm going to show you. Well, there it is right there. There's light. I'm going to show you in red, and I'm going to show you how we got these particles. So there will be no confusion anywhere. What is an electron? An electron is half of a photon. That's a photon. You take half of that away, you have an electron. That baby wants to incorporate into at least another electron to bar back-to-back magnet-like, so that when it hits something, it bounces off. When they're one of them at a time, which is an electron, and not a photon, singularly, they will invade and cause heat and devastation. If there's enough of them at the same time, they will kill you. Photons, if they bang into you the same quantity of photons, they're going to bounce off you. You're just going to be brightly lit up. This here, you're going to be brightly exploded. Now, what is a proton? Well, a proton, one big solid positive ball. No, absolutely not. And they know that's not true. Absolutely, no, and no question whatsoever, they know it's not true. They just have no way to explain it. Because they say, oh, well, you get these beta decays and you get this little, you know, a neutron can turn into a proton, and then they decay into isotopes and so forth. So where did decay come from if it's just one gigantic proton? It's insanity. So forget that whole thing. The proton is made up of 1,837 of these. That's the weight of a proton, is one atomic mass unit, and an electron, they claim, is 0.0005854, something like that. So if you divide it, it ends up being 1,837 of the weight of the electron equals one proton. And then one additional electron, exactly, adds to 1,838 electrons, which makes a neutron, which becomes neutral because it's got an equal number of electrons in it. If you don't have an equal number of electrons, you have something that is magnetic, basically. It's attractive or repulsive. And from my research, I discovered that the protons are hollow in the center. And I can virtually prove this. I'll show you what I'm talking about. In actual experiments, not just guesses. That's an experiment. Rod Warren did this. I've been working with him 5-6 years. And this is green. Let's go further. And I'm going to show you that can separate. Watch this. That could separate. The red ones are the same. And here's the red ones. coming through the venturi, and they were in that same configuration, and now there's a black balls roll away from the white. The white becomes explosive electron showers. The black ball, which they know exists, they just don't know where it came from, is called a muon, and it was attached, as you saw, in the photon configuration, and they come apart. That is raw energy. I'm telling you right now, I believe that is harvestable raw energy. Literally millions or at least thousands of times more energetic than it was before it hit the venturi. Passive, non-interactive venturi. Strictly a crusher of particles. Okay, this is literally all that's happening here. You saw these balls, they're gigantic balls. There's a particle in the center. The wave is way out here. Boom, 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 boom. And what are they doing? They're stacking up. These huge balls, the particles got to go through there. Well, the black part of the particle says, I'm not going. So I'm getting out of here. And they get away. Those are the muons. And I believe it's dark matter. Nobody ever knew there was a dark particle attached to an electron. Nobody ever knew that. They thought an electron was that bright, glowy, powerful, energetic particle. And it is. But it has this dark side, literally. Now, what happens at the venturi? When this thing hit, as you know, the white sprayed through here, which is the electron showers, the electron neutrinos they call them. These are the muons, muon neutrinos. When they're attached together, it's nothing more than an electron and a muon sitting together as a particle like that, an electron and a muon. They don't know that they're together. They see them both, they just have no clue they're together. Now, I know they're together, and I know two of them together make into a photon. And we see them absolutely separate here. So we know the muon part was originally part of an electron. Now it's on its own. I never imagined this could be possible, but I see it, so I can't dispute it. And what CERN sees is nothing but a bunch of debris. They use 100 billion particles. We use the light, which is only a couple of particles. And so we see the actual division of the particle, and we see the particle. CERN sees all the debris after years and years and years of searching through garbage. They see them, but they have no clue where they came from. So I'm here to help you, CERN. All right, you saw the green electron. That's the same, photon. Same thing, only these are red. And they're not as nearly as energetic, and I can prove that as well. And when they come in, they're not really descript until they start to concuss just prior to separating. Then you see them, all I can say is like a magnet forcing into another magnet or particle into another particle, creating a glow. And you can see it's creating more and more of a glow as it hits there, and then it just explodes into particles. Now what you just saw is the the red photons, and up above here this is how the whole thing starts. You have that photon way back here. That particle controls this wave out here. There's another particle controls that wave. Another particle back controls this one. This is a pulsed red laser. As it reacts with the space directly in front of the first pulse, these particles here have to concuss. When they concuss, they glow. That's the nature of push to shove of photons and electrons. In strictly electrons, you get real, like electricity. You get, static and lightning and all that. This is a little bit different because you have the particles attached together, and it doesn't seem to have as much of a concussive effect as, well, obviously static and lightning and all that. You know how that works. Light is obviously much less aggressive. However, it's literally the same thing. Only it's complete photons instead of separated electrons. That's the difference. Now, so here's the wave, there's the particle. So here you have particle-wave duality. Oh, they always talk about that, and that's a big mystery. Now, then they say light can't accelerate. Well, I can tell you it accelerates quite easily. That was that wave. The particle, as I talked about, was way back here. Now the particle is being accelerated, and the wave is being stretched forward like a jet fighter, reaching Mach past 1. Zip! Out. Out it goes. The wave stays back here. The particle goes, explodes, separates, complete electron showers, complete muons. Then they reattach. This is a single slit. This has nothing to do with interference patterns. Totally, they're wrong about every single thing they're saying. 100% wrong. 100% wrong. All right? And they attach back here, and these are the muons. And I'm going to tell you right now, that is dark matter. Okay, you see what you just see in here? From 0 to 1 is 1 second of time. And if there was one cycle of, like that big long one, that's 1 hertz. See, 2, 3, 4, it's coming up to 5 hertz. There's 5 waves. There's 1 wave is 1 hertz, 2 waves, 3 waves in this amount of time. Now, let me show you something else. All right, what you're going to see here is amazing resonance experiment, BrustPup, fabulous, 16.5 million hits, and probably half of them are mine. I love this thing. Watch. This is 100 hertz. Now, we were just looking at 1 hertz in 1 second is 1 wave. So we're taking 100 of these waves per second. Now, as we increase those waves up, what they do, when we're talking about hertz, we're talking about shake this way, shake. So it pushes, shoves, pushes, shoves. Poop, 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 poop. That's called alternating current. Push, shove back, push, shove back. That is alternating current. DC says send my electrons that way and don't go back. AC says alternate. Go this way, send them back. Go this way, send them back. And that shakes everything just as like DC current does, only you have to work with it in a different way. You have to rectify it. And this was my background. I know this very, very well. And here's what's going to happen here is this is going to shake these salt molecules. Now, what is salt? Salt is NaCl. What does that mean? It's magnetism. It's a bar magnets, basically. They're on both sides of the periodic chart. One of them has a ton of extra electrons, and one of them wants electrons. So they're basically a bar magnet. What does that do? When you shake them with these frequencies, they get crazy. But all of a sudden, at a certain frequency, bam, they lock in. Let's watch. All right, you ready? Here goes. BrustPup. Amazing resonance. If you want to find the secret of the universe, think in terms of energy, frequency, and vibrations. Nikola Tesla, the best of the best. Now, here's what's going to happen. This is that salt table. And that table is hooked up to this machine, which is sending these frequencies in here. Now, they're going to put salt on that table. They're starting out at a very low hum. Salt. That's our little bar magnets. They're just laying around doing nothing. Now we're going to vibrate it. They say vibrate it. But whenever you vibrate something, vibration is nothing more than push to shove of electrons. So that's what they're doing, is they're pushing to shoving these electrons back and forth. Vibration in this case is alternating current. As the pitch of the tone increases, the patterns will form. And they form at exact resonances. Watch this. 345 hertz. Bam. What are we seeing here? 345 hertz. That's 345 cycles in 1 second. They just all of a sudden, bam, they lock in at this. That is the smallest particle that exists. It's like hydrogen. It has a central core, and it can have just a very limited number of electrons around it. Now watch what happens as it goes up. You see how nicely it shapes as it hits that frequency? In between those frequencies, you have isotopes. Now you go up to the what they call the zone of 8, or I forget what it is. Well, there's eight stable patterns outside the core. Now, before I said the electrons were literally hollow, or the protons, I'm sorry, were literally hollow. These would be considered, in my world, these are the protons of the nucleus of a atom, and that each one of these would be considered a proton. And it's hollow in the center because the negative attractiveness part, which is that muon, which is the dark matter, is literally gravity, and it's pulling as many particles as it can until it becomes stable at that frequency. And we are being resonated. We have tons of resonance, Schumann resonance frequencies all the time, and the universe itself has a universal hum. This is nothing accidental. And so these are, oh boy, the rule of 8. That's what I'm telling you, when you get old, things it gets hard. Anyway, the rule of 8 says that stability will occur when an atom is in this zone of 8 range, which is the valence shell has 8 stable electrons. Now, in my world, though, that is not one proton. That's 1,837 electrons. So we got a whole new way of thinking to do. And you can see it. It goes up. They get extremely sophisticated patterns as you go up. You see it? Look at this. And these are just more and more frequencies. The higher the frequency, it will lock in at a stable frequency. You see it? Boom. Stable. Boom. There's that pattern of 8 again. 1, 2, 3, 4, 5, 6, 7, 8. And then there'll be, I mean, it's got something to do with the nature of the universe and this push to shove of electricity. All right? That is the nature of the nucleus. And then surrounding it will be little tiny electrons. It'll be in a soup of electrons surrounding it, and it will influence a certain number of electrons in that soup. And as that soup gets heated up, just more and more electrons come in. That's what the heat is. That's all it is more and more electrons. And each one of these zones, these proton zones, is 1,837 electrons. So there's a whole batch of floating electrons going in. When it gets cold, they move to where, they move out. And then it gets cold. So they go to a place where it wants to take those electrons, and this region loses the electrons, it gets colder. If you force electrons in, it gets hotter. It's very, very simple when you break it down to electron flood theory. Okay, I just showed you all of the shaking and the particles and so forth. I say that is what every proton looks like. And as you build those protons, those are what made those molecules into those little regions that's surrounded with the rule of 8. Now here he's got 6. Well, I'm just going to let it play and I'll explain it as he goes along. Here it goes. All right, there's that core. Now, he's got 6, boom. Now, you see what happened? This wants to attract 2 there. So this is negative or positive, and this is positive or negative, but it's one of each or the other. Now, watch what happens when he puts it into the center. It creates, he's going to turn it around and put the opposite polarity in the center. So now, at this point, what he just created was this right here. The negatives in the center, which is, well, they're not negatives, I'm sorry. They're really positives. The muons are in the center, and the electron blasters are on the outside. So here's what goes on now. He's got the core of a nucleus now, and now he's going to let some electrons flood into it. So now he's going to let some electrons come bouncing in. Watch what happens. Boom. That's what an electron does. And he can drag that around all day long. So there's no physical attachment. But there is this. There's that, really, is what's going on there. And it's going to come around with it. They're the magnetic attractive entanglements. All right? And there will be, see, it's between the two of these. So it's an entanglement. It's almost like grabbing it and holding on to it and saying, come on over this way. And it does. It stays between. Watch as it goes. You see it? You see it? It's right in between those two magnets. And there'll be another one you could put here and another one. And he does. You'd have to watch this whole thing. But now it's going to shake it around until he bounces it as it gets energetic. Now it's going to start to get energetic, and it'll get a certain distance away, and it'll come back, and it'll stay in there, and I'll say, boy, I'm getting hot, man, I'm going to break down. Oop, I just broke down, and I am now going to turn into nuclear decay. You keep doing that, I'm out of here, I'm going to go. That's it, I'm done, case closed. Okay, so let's just round it up. We had a muon, which is the muon neutrino. CERN knows they exist, no clue where they come from. They also found electron neutrinos, which create electron showers, which is the white ball, that's the black ball. I showed you these, I showed it to them. And I say 1837 of that particle makes up a proton. And that proton has a hollow core, I showed you that as well. This is the insane thing. They know that by this process, unstable atoms obtain a more stable ratio of protons to neutrons by getting rid of electrons within their nucleus. They're saying the electrons are spit out from the neutrons. A neutron can go to a proton to a neutron, simply by adding or removing an electron, which is part of every single molecule, every single atom, every single thing that exists is made of only electrons. That's my statement. Okay, I showed you it was a particle. I showed you it was a wave, and the particle was back creating the wave of magnetic influence. I showed you the light accelerates. It gets pulled through a venturi. I showed you that these are the electron showers coming through. We're seeing these coming at us. This is a particle that no one knows exists. And I don't know what it is, but it appears to have been a reverse spinning particle that interacted with the Higgs field light electron particle and created a semi-electron particle. This is as deep as it gets. We're deeper than CERN. This is a right-hand spin of a blue electron and photon, and it drifts to the left as it goes flying, and one pulse takes all these at the same time in its oscillating state. It appears to me, that's what I'm saying. And it absolutely deserves to be investigated. I've been looking at this for 5 years, tried to contact everybody. I even took a course at University of Geneva and showed this to them. They said, ooh, that's fascinating. And that was the end of it. So I don't know what to do about how to get anybody to pay attention to anything anymore. Once they realize you can back up what you say, they don't want to talk to you.